Professor Belfrost's science class is back.
Hi, welcome back to this channel. And today we'll again discuss another concepts related to science. So here's the science tutorial for you today. Are you ready? Let's continue playing this video. Okay, so this is the second lesson on the chapter of stoichiometry on the chemical reaction. So let's continue from our last episode, which is here. Okay, this is point five. Now we enter point five. So yeah, actually we have some reaction to deal with, and the first one is ionic reaction. Later we'll also see about redox. Okay, reduction, oxidation, and yeah, the first one we'll deal today is ionic equation. Okay, so that the, given the abundance of water on Earth, that it stands to reason a great many chemical reactions that takes place in the aqueous media. And when ions are involved in these reactions, that the chemical equations may be written with various levels of detail appropriate to the intended use. And let's see the reaction that takes place in the aqueous solution as shown in the slide. For example, we have aqueous solution of the CaCl2 and AgNO3. Okay, they are mixed together and the reaction takes place to produce Ca 2 times NO3 and solid AgCl. Okay, this balanced equation is derived in the usolation, and it is called a molecular equation because it doesn't explicitly represent the ionic species that are present in the solution. What is ionic species? It means that, for example, CaCl2 will split it to Ca2 plus and 2Cl minus. That is the ionic species that's meant. Okay, that when ionic compounds dissolve in water, that they may dissociate into their constituent ions. Okay, but sometimes also, yeah, so we need a very we need to pay attention to these ionic compounds. Ionic compounds can dissolve in water, whereas for the covalent it cannot. Okay, so yeah, so it can dissociate into their constituent ions and subsequent disperse homogeneously throughout the resulting solution. So ionic compounds dissolved in water are therefore more realistically represented as the dissociated ions. For example, this case, okay, you see the aqueous one, CaCl2 becomes um, the calcium ion plus 2 chloride ion. Then we have the 2 AgNO3, okay, it becomes 2 silver ion and 2 nitrite ion. And we have CN3 two times, it becomes 1 calcium ion and 2 nitrite ion, okay, 2 nitrate ion. Okay, so unlike these three ionic compounds, that the AgCl actually doesn't dissolve in water to a significant extent. Okay, and it is signified by its physical state notation, which is S. Okay, so only the one that represented with Ag is dissolved in the water. Okay, and explicitly that represent all the dissolved ions results in a complete ionic equations that we can rearrange by writing down by replacing this um, uh, respective chemical formula with its ion species. Okay, for example, CaCl2 to be Ca2 plus and 2Cl minus, and the other follows. Okay, so we have seen so far that by examining this equation, that we know that we can eliminate some. For example, for Ca2 plus, it exists on the left side and right side, so we can eliminate it. It's like mathematics. Okay, for example, we have 2NO3 minus, and also we here have 2NO3 minus. We can also eliminate it. Okay, so yeah, we can eliminate the one that is in identical form. How about if they are exist in different coefficient? For example, we have 3Cl minus here, but yeah, say that, okay, in this equation it's not like this, but say that one day we find out that this 3Cl minus in the left side, and for example 2Cl minus in the right side. So yeah, we still eliminate it, but um, to the smallest extent. I mean, the smallest extent is because we have 2Cl minus here, we have 3Cl minus it, we are eliminated by 2Cl minus for the both side, and we left with 1Cl minus in this left side. That's the example. I mean, okay. So these spectator ions Ions whose presence is required to maintain charge neutrality are neither chemically nor physically changed by the process, and so they may be eliminated from the equation. So the previous one, Ca2 plus and 2Cl minus, I mean Ca2 plus and the 2NO3 minus, is called spectator ions, and they may be eliminated from the equation to yield a more succinct representation that's called a net ionic equation. And here's the simplified one, which is 2Cl minus plus 2Ag plus results in 2AgCl. Okay, and because you see the coefficient 2, 2, 2, we can further simplify it to the smallest possible integer, and it creates Cl minus plus Ag plus yields AgCl. And this net ionic equation indicates that the solid silver chloride may be produced from the dissolved chloride and the silver 1 ion, regardless of the source of the ions. So now let's dive more about this by examining the example on this one. So about ionic and molecular equation. So when carbon dioxide, CO2, is dissolved in the aqueous solution of the sodium hydroxide, which is NaOH, okay, the mixture reacts to yield aqueous sodium carbonate. Sodium is Na plus, while carbonate is CO3 with the charge -2. So it will create Na2CO3, liquid water with H2O, and we need to write a balanced molecule, complete ionic and non-ionic equation for this process. So you just need to follow the previous steps. First, you need to write down the unbalanced one first, okay, unbalanced chemical equation, and then we need to balance it, okay. And in this case, the balancing process is actually quite simple. It's quite straightforward. Okay, we see that we need two sodium atom here, so we need to multiply this NaOH to, okay, I mean sodium hydroxide to 2, the coefficient is 2, we place coefficient 2 here, but yeah, we see if it disrupt the other stability balance. We have 2 hydrogen now here, and also we have 2 hydrogen here. How about the oxygen? We have 3 plus 1, and here we have 2 plus 2. Okay, this is balanced now. And now the 2 dissolved ionic compounds that we can find there, actually 3 ionic compounds that we can be dissolved is that oh yeah, only 2 ionic compounds that can dissolve here, because CO2 is not, it's covalent, only ionic compound, okay. Though this is aqueous too, CO2 is aqueous too, but this cannot be dissolved because this is a covalent, only ionic compound can dissolve, okay. So we have sodium hydroxide that will dissolve into the sodium ions in the hydroxide ion, as shown, 2Na plus 2OH minus, and sodium hydro what is sodium carbonate, I mean, to dissolve to Na plus CO3 to minus. And after this, we eliminate the 2Na plus and 2Na plus, and this is the only thing that we can eliminate. And we get the net ionic equation, which is CO2 aqueous plus 2H minus aqueous yields CO3 to minus aqueous plus H2O liquid. Now, I want you to try to solve this one, this equation. I'm sorry. So, you see, we have salt here, table salt, NaCl, sodium chloride. Okay, and we have yeah, we have sodium chloride, we have water, and we give electricity, and it will produce sodium hydroxide, hydrogen gas, and chlorine gas. Okay, so you are asked to create the balanced molecule. Okay, you need to balance it first, and then complete ionic and non-ionic equation for the process. Actually, this is not very difficult. I left this for you to solve it by yourself. Now, point 6 is that another reaction. Before we have dealt with ionic reaction, now we dealt with a precipitation reaction. What is precipitation reaction? Precipitation reaction is one in which dissolved substance react to form one or more solid products. And yeah, it involves the exchange of ions between ionic compounds in the aqueous solution, and or sometimes referred to as double displacement, double replacement, or even metathesis reactions. These reactions are common in nature, okay? And yeah, also this is widely used in industry, okay? And precipitin reactions also play a central role in many chemical analysis techniques. So the extent to which a substance may be dissolved in water or any solvent is quantitatively expressed at its solubility. So we learn new term here today. We have a solubility, which is defined as the maximum concentration of a substance that can be achieved under specified conditions. And substances with relatively large solubilities are called to be soluble, and the substance will precipitate when solution conditions are such that its concentration exceeds its solubility. And substances with relatively slow solubilities are said to be insoluble, and these are the substances that readily precipitate from solution. Okay, let's see the solubility of many ionic compounds. Okay, so soluble ion compounds is the compounds that contain these ions. We have ammonium, we have group 1 cation, we have lithium, sodium, potassium, rubidium, cesium. Okay, there are no exception for this group. But for the anion, this is halogen, right? Halogen, chlorine, bromine, iodine. Okay, and the exception is that if this kind of anion makes compound with argentum, silver, okay, ion of silver, and the hydrogen, okay, and also the plumbum plus 2, okay, lead, okay, lead 2. Also we have fluorine, okay, and the exception is with compound with group 2 metal cations, okay, you know, 2 metal cation bases, yeah, you need to know it. So plumbum 2 plus, and also 3 plus, okay, iron 3. So the ionic compound is soluble is the one with this C2H3O2 minus, also have H3O3 minus, NO3 minus, okay, nitrate, okay. So we have ClO3 minus, okay. I guess this is perchlorate or something, okay. And then no exception for this group. So the last one is sulfate, okay, and this also have some exception that it cannot apply with the compounds with the ion of sulfur, barium, calcium, the hydrogen, plumbum 2, and SR. I think this is strontium, right? Okay. And insoluble ionic compounds, okay, is the one that contains this ion, okay, carbonate, CrO4 2 minus, okay, this hypochromate or what, and PO4 3 minus, which is phosphate, C2 minus sulfide. And the exception is that compounds with group 1 cations and for ammonium, and also contains the hydroxide. Okay, but the exception is that it compounds with group 1 cations and with barium ion. So yeah, you may need to print this table. Okay, I didn't ask you to memorize this all because it's actually quite difficult. You may, if you when you need to solve the problem, you may refer back to this table, but actually you need to try to memorize some of them, or maybe after some types of practice you will get used to it. Okay, so yeah, a vivid example of precipitation is observed when a solution of potassium iodide, okay, potassium, this is K, iodide is I minus, okay, so Ki, okay, and then lead nitrate, lead is Pb2 plus, nitrate is NO3 minus, so PbNO3 2 are mixed together and resulting in the formation of the solid lead ion, okay, Pbi2, and also potassium nitrate, okay. And yeah, here's the solubility guidelines. That the uninsoluble compound among all of this info is the lead iodide, and one of the exceptions to the general solubility of the iodide salt. Why? Let's see. Iodide salt, okay, I minus, okay, so it's not soluble because it reacts with Pb2 plus. Okay, so yeah, it may be used, the table before, used to predict whether a precipitation reaction will occur when solution of soluble ion compounds are mixed together, and one merely needs to identify all the ions present in the solutions and then consider a possible cation pairing could result in an insoluble compound. And for example, that mixing solution of silver nitrate and sodium chloride will yield a solution containing all the ion of silver ion, nitrate ion, sodium ion, and chloride ion. And aside from the two ionic compounds that originally present in the solutions, that the second one, nitrate and sodium chloride, two additional ionic compounds may be derived from this collection of ion, which is the sodium nitrate and the um, yeah, silver chloride. Okay, so the solubility guidelines indicate that all natural salts are soluble, but that the silver chloride is one of the insoluble one. And here is the precipitin reaction that predicted to be occurred. Okay, so NaCl plus AgNO3 results AgCl plus NaNO3 and can be simplified to be Ag plus Cl minus results in AgCl. Let's see the example for this one. So predict the result mixing reasonably concentrated solution of the following ionic compounds. If the precipitation is expected, write the balanced net ionic equation for the reaction. Okay, so we have the first one is potassium sulfate and barium nitrate. Okay, so potassium it is K. Okay, sulfate is SO for 2 minus. Okay, so yeah, we just need to switch place, right? K plus SO4 2 minus, and the one is Ba2 plus and NO3 minus. So it means that we need to pair barium with sulfate and potassium with a nitrate. Okay, so potassium with nitrate, it will mix KNO3. Barium with sulfate, because both have -2 charge, it will cancel and it results in BaSO4. Right? So yeah, the solubility guidelines indicate that the BaSO4, I want to check the table for 4.1 again, is actually insoluble, and so a precipitation reaction is expected. And the net ionic equation for this reaction can be derived as shown. Okay, which is for the BaSO4 itself, okay, which is Ba2 plus SO4 2 minus results in BaSO4. How about B, lithium chloride and silver acetate? It means that we need to pair silver and chloride together and lithium with acetate together. Lithium is Li plus, acetate is C2H3O2 minus. So LiC2H3O2 is lithium acetate, and silver chloride is, because silver is Ag plus, chloride is Cl minus, is AgCl. So you see that AgCl is insoluble, so we expect that it happens a precipitation reaction. So the net ionic reaction is Ag plus Cl minus results in AgCl. Next, lead nitrate and ammonium carbonate. It means that we need to pair the ammonium and nitrate together. Ammonium is NH4 plus, nitrate is NO3 minus, which is NH4NO3. You see the second one here is, and lead and carbonate. Lead is Pb2 plus here. Okay, and carbonate is CO3 2 minus. Okay, actually there are many lead too. Okay, so Pb and CO3, PbCO3. And we see that the scientific guidelines say that PbCO3 is not soluble, or insoluble. So we expect this to make a precipitin reaction, which is Pb2 plus CO3 2 minus becomes PbCO3 solid. Okay, the result of the precipitation must be solid, and the left side must be all aqueous. Now I want you to check your learning by solving this problem. Okay, next one, the last one for today, acid-base reaction. We will continue on redox on the next episode. So for acid-base reaction, so an acid-base reaction is the one in which a hydrogen ion, which is H plus, is transferred from one chemical species to another, and such reactions are of central importance in numerous natural and technology processes. Okay, and the subject of acid-base chemistry is worthy of thorough discussion, a full chapter, but actually, because we just want to discuss a little this time, we'll just take the important part, because actually we have dedicated chapter for explaining this acid-base reaction. Okay, so take place. We need to understand that in this context is an acid. Okay, so we see that, for example, in this book, I'm sorry. Yeah, here's the equation. Oh, an acid. I need to explain first. What's an acid? An acid is a substance that will dissolve in water to yield a hydronium ion, which is H3O plus. Like for example, like this, we mix, okay, we react the chloric acid with water, and it yields us with chloride ion and hydronium ions. Okay, and the process represented by this equation confirms that hydrogen chloride is an acid. Okay? Because when it dissolves in water, the hydronium ions are produced by a chemical reaction in which that the hydrogen ions are transferred from the hydrogen chloride, okay, chloric acid molecules into the water molecule, okay, as shown in the figure. But the nature of the chloric acid is that it's such that its reaction with water, as just described, is essentially 100% efficient, and virtually every chloric acid molecule that dissolves in water will undergo this reaction. And acids that complete react in this fashion is called strong acids, and one of them is HCl. Okay, but yeah, a far greater number of compounds actually behaves as a weak acid and only partially react with water. Okay, and weak acid are commonly encountered in nature. Okay, for example, this one we have acetic acid. Okay, which will react with water. Okay, you see this symbol? It means that this is not yeah, truthful. I used to say truthful reaction. It means that the reaction sometimes go forward, sometimes go backward because it cannot um, yeah going dissolve completely. Okay, and yeah, you see that we have CS3CO2 minus here and H3O plus. Okay, actually partially it also dissolve into hydronium ions, but mostly it's not. Okay. Okay, so here's the guidelines table that show you the common strong acids. So we have hydrobromic acid, we have hydrochloric acid, we have hydroiodic acid, we have nitric acid, we have perchloric acid, and we have sulfuric acid. Okay, we have done with base with acid, and now we enter base. What is base? A base is a substance, okay, that will dissolve in water to yield the hydroxide ions or OH minus. And this is the most common. The most common bases are the ones that comes from alkali or alkaline earth metal cations, which combine with the hydroxide ions. For example, the sodium hydroxide and the calcium hydroxide. But unlike the acid compounds discussed previously, that these compounds do not react chemically with water, and instead they dissolve and dissociate, releasing hydroxide ions directly into the solution. Okay, and yeah, for the one that is told to be so, this is called strong basis, which is the basis that completely dissociate in water. So consider the reaction, the dissolution of the lye or sodium hydroxide in water. So we have sodium hydroxide which dissolved into sodium ions and the hydroxide ion. This equation confirms that the sodium hydroxide is a base instead. And when dissolved in water, the sodium hydroxide dissociates and it yields sodium ions and hydroxide ions. And this is also true for any other ionic compounds that contain the hydroxide ions. Okay. But unlike ionic hydroxide, some compounds produce hydroxide ions when dissolved by chemical reacting with water molecules, and in all cases, this compound react only partially, and that is called the weak bases. For example, this one. See, when dissolved in water, the ammonia NH3 reacts partially to yield hydroxide ions. Okay, so this is called the weak base. Okay. So, what is a neutralization reaction? A neutralization reaction is a specific type of acid-base reaction in which the reactants are an acid and base, but not water, and the product are often a salt and water. So, acid plus base reacts to make salt or water. For example, we have the magnesia, milk of magnesia, which is solid, which is aqueous suspension of solid MgOH over time, and when it is reacted with hydrochloric acid from our um, uh, digestive juice, I mean the stomach acid, it will produce this MgCl2 and two water, two molecule of water. Let's see example to make it clearer. So writing equations for acid-base reactions. So we need to first write balanced chemical equations for weak acid hydrogen. Yeah, it's been highlighted here. Weak acid hydrogen hypochlorite. So yeah, you need to know first what is hypochlorite. Okay, so hypochlorite is actually ClO minus, but most of the time books will write it as HOCl, not HCl. Okay, I don't know why. Don't ask me. Okay, HOCl and water is H2O. It's very straightforward. But because this is a weak, so it only partially react. Okay, so you need to have this symbol with you. Okay, so HOCl plus H2O will, yes, actually this is ClO minus. It's better written is ClO minus plus H3O plus. Okay, we need to have H3O plus. Okay, only partially dissolved. But how about this? A barren hydroxide. This is a base also is neutralized. Okay, so this is neutralization reaction. Okay, so we have BaOH2 or OH, okay, hydroxide ion two times, and it's NO3. And since this is a neutralization reaction, that the two products will be water and start decompose of the have the ionic hydroxide and the anion generated when the acid transfer into the hydrogen ions. Okay, which gives us with BaOH2 plus 2HNO3 results in BaNO3 two times plus 2H2O. Okay, great. Now I want to check your understanding. Please solve this equation. Okay, so neutralization of any strong acid with an ionic hydroxide. Okay, here's the answer, but I want you to find out why it can come with this solution. Okay, so here's a little quote for you today before we end this episode. So, dream as if you'll live forever and live as if you'll die today. This is the quote from James Dean. That's the end of the video for today. Thanks for watching, thanks for following so far. And here's what you need to do. Please subscribe, give a thumbs up, comment, and share this video to your friend. And also, don't forget to check our website at https://science-exploits.uanaux.com, and I'll be back on every Tuesday, so keep watching and be thoughtful. Goodbye, see you on the next episode.